Okay. So what was the requirement of the fun event to be fun? Attend all the lectures. Yes, I mean you are all attending, but then pay attention. Okay. So I hope you paid enough attention to all the lectures, or not lectures. I shouldn't say lecture. All the talks, uh, and then we'll see what is the fun event. So any guess what is the fun event? Quiz. Then let's have quiz only. Okay, maybe, I mean, it's not a very bad guess, I'd say. We'll see what's the fun event. And then hopefully we'll all join for the dinner. Okay. Okay, so with that, any question before that? Apart from what is the fun event? Okay, fine. With that, let me welcome Gopal. Gopal received his BTech in Electrical and Electronics Engineering from the National Institute of Technology Calicut in 2010. He subsequently received his Masters in Computer Engineering from North Carolina State University, Raleigh, NC in 2012, and PhD in Electrical Engineering from Purdue University, West Lafayette, Indiana in 2019. He is currently an assistant professor in the Department of Computer Science and Engineering at IIT Madras. His research entails developing bioplausible machine learning algorithms and hardware architectures for energy efficient computing at the edge. Over to you, Gopal.
Alright, so am I audible? Alright, so thank you so much for the introduction and very good morning to everyone. So it's Sunday morning, so let's try to make it interesting for all of you. Can we switch the... Okay, so the title of my talk today is Energy Efficient Neuromorphic Computing using spiking neural networks. I think there are a couple of buzzwords here, right? Neuromorphic and spiking network. So let's kind of delve a little deeper into those, and then hopefully we have some takeaways at the end of this talk. Okay. So essentially, I stumbled upon this field of spiking network while I was at Purdue to pursue my PhD, and then the motivation behind looking at like an alternative or future computing paradigm is primarily stems from energy efficiency, right? So all of us want to run AI and ML algorithms, right? But we also want to minimize the carbon footprint. So essentially, the first time I heard the term machine learning was during my, at the end of my undergrad in 2010 when IBM came up with this Watson, which was an AI agent. I don't know whether they called it an agent, but it was a robot that could defeat the human champions in Jeopardy. Jeopardy was an American game, right? And then from that point on, the deep learning momentum caught up. And the second time it made to the press was when Google DeepMind, they released AlphaGo, right? So it defeated the then human champion, Lee Sedol, right? And then now we have ChatGPT. ChatGPT is just a name, right? We have numerous apps, like, built based on the foundation models, right? Which even supersede our human performance in a lot of the tasks, right? So the question really is, what is the cost, to achieve this high performance? Looks like, most of those, large models, they consume, at least in orders of magnitude more, energy or power compared to the human brain, right? Which is one of the most, efficient machines under humankind, right? So we can debate that number, but I think the accepted fact is, okay, so our brain, does a lot of processing, all the time, including when you sleep, right? But still we don't burn it, right? So it's still, energy efficient in some regard. So the motivation was to kind of, take inspiration from some of the, computing principles, from whatever little we know about the functioning of the brain, and build a useful, practical computing paradigm with that, right? That's kind of the goal behind this field of neuromorphic computing. Okay, so the formal definition is, okay, as I said, you have neuroscientists who are trying to figure out, what is, how is the brain able to learn? How is the brain able to make those predictions? How is it, responding to various, tasks that we have, right? And then we try to abstract out those principles and then build a computing model at the algorithm level, as well as the hardware that we want to build. Also, we want to draw some inspiration from the brain, and that's something I'll talk about towards the end of this presentation, right? So essentially, neuromorphic computing is, okay, take those principles and build algorithm as well as hardware that has some inspiration, so that the goal is not to just copy and mimic what is there. Rather, the goal is to take those principles and see if you can build something useful, which offers you some something more in terms of, let's say, energy efficiency or security or robustness. We'll look into that a little later. So this field itself was pioneered by a professor at Caltech called Professor Carver Mead, who in the 80s, when the so-called von Neumann computing was taking shape, so Professor Carver Mead was trying to understand some of the neuroscience models, and he was kind of building these mixed signal circuits that would mimic the functionality we have, right? That's how this field still got started, and some of his works include the initial dynamic vision sensor cameras, some of the circuits for modeling the cochlea in your ear and so on, right? So why kind of neuromorphic computing now, right? So a lot of the folks who work in this, as I said, they try to figure out if this paradigm can perform reasonably well in the tasks that we care about, right? It could be classification, right? It could be detection, but along with that, okay, can you do it with improved energy efficiency, right? That's kind of the underlying goal. And usually maybe things are changing, but if you have those large language models, or most of them are kind of deployed on the cloud, and then that's where the inferencing happens. So let's say you want to have more and more intelligence towards the edge devices, right? That includes your anything starting from your, let's say, mobile phones to very low cost microcontrollers, or even your sensors. Sometimes you want to embed intelligence in them. So if you want to kind of have some kind of intelligence or intelligent computing in those edge devices, neuromorphic computing has a promise of improved efficiency, right? So that's why I think it's all the more relevant today. Okay, so let's, before we delve into any network architecture and so on, so let's try to understand what is the basic building block if I were to have a network that abides by some of the neuromorphic principles, right? So at the outset, we are going to use something called a spiking neuron as a building block in the network. The loose parallel you can have, if you have done some machine learning or deep learning, is so on neural networks you typically have something called activation functions, right? ReLU, sigmoid, tan, hyperbolic, and so on. So you can think about the spiking neuron as one other kind of activation function. Okay, so essentially what happens is, on the left I'm showing a biological neuron where you have an input neuron called a pre-neuron, which is connected via a synaptic weight or a synapse to a post neuron or an output neuron. Similarly, as far as the spiking neuron is concerned, you have a bunch of input spiking neurons. When I say spikes, they emit zeros or ones, right? So the spikes don't have a level per se. They could, but for all the works I'm going to show, it's an impulse, right? You either have it or you don't have it, 0 or 1. So you have those input spikes that come in, they get modulated with the synaptic weight that you have between each of those input pre-neuron to the corresponding output post neuron. So you kind of then accumulate that sum into a state variable in your spiking neuron. The state variable is usually called a membrane potential, right? So you kind of accumulate this weighted input sum into this membrane potential, and you compare the membrane potential with the threshold at any given point. If the membrane potential exceeds the threshold, the post neuron emits an output spike. So the fundamental building block of a neuromorphic neural network or a spiking network is the spiking neuron, where you take in input spikes and you produce output spikes. Okay, essentially if you have a network that is built using these spiking neurons, the fundamental operation that you do here is an accumulate, right? Because the inputs are zeros and ones. Okay, and then you just have to multiply zeros or ones with any floating point or quantized integer weight here, so that ultimately you don't have a MAC or multiply accumulate, rather you have an accumulate operation. In deep learning, usually you have a MAC operation. You have input which could have let's say 8-bit int, or it's a 16-bit floating point, right? So you have to do a multiply and accumulate. Rather, the spiking network, you just have spikes at the input, and hence usually you have only the accumulate operations here. That's one way you could say, okay, you can derive some kind of efficiency, because implementing an adder is more efficient than having a multiplier and an adder together. Okay, and the second thing we need before we delve into a network with spiking neurons is, okay, so most of the real world information, right? You take a picture, we have real values, right? Let's say pixels will have R, G, and B, and each dimension or each channel you have, let's say, pixel values ranging from 0 to 255. So if I were to feed such an image or to a network, there are also need to figure out how do I encode that real information to spikes, right? So there are very two popular kinds of coding methods here, right? One is called rate coding. Essentially you say that okay, I want to encode a real value, let's say 5 or 10. The way I'm going to do it is I'm going to produce n number of spikes over some time steps, right? If I were to represent the value 6, maybe if I run 100 time steps, I want to produce 6 spikes, let's say. Okay? Essentially, you are saying that the firing rate or the average spiking rate of your neuron is proportional to the real value that you are trying to encode. Right? This is called rate coding. So one way you can translate a real value into a spiking rate. The second approach here is called the temporal coding. So you say that okay, I want all my neurons to spike only once, but the way I'm going to encode the real value is by the virtue of where I plant those spikes. So in the sense, the spike timing difference between any two pairs of neurons will be proportional to the difference in the real value. Essentially, you are saying the real valued information is encoded in the spike timing information, right? So temporal coding is, as you can see, is much more efficient, from a algorithmic or hardware standpoint, because every neuron would spike only once or it will not spike at all. But then you are still able to, encode all the continuous information that you have. But unfortunately, it's not unfortunate, but it's kind of very hard to get it to work and build a lot of useful computing models and get a good accuracy. So mostly rate coding is kind of a preferred approach because it has a straightforward correspondence to how you encode the real values, but a lot of work of late is also going into how can you now employ temporal coding and in neuromorphic computing so that you can also have efficiency which is much more than what you have with rate coding techniques. Okay, is that clear? So essentially you have a spiking neuron, okay, which will take in input spikes, produce output spikes. The second aspect is okay, you have a real world value. How do you now encode it to a spike train, right? So we saw kind of two approaches here. Rate coding, very intuitive. Number of spikes over time is proportional to real value. Versus okay, temporal coding, the value is encoded in the spike timing difference. Okay. Yeah.
What time reference you take in temporal?
I mean, you start from zero, right? Let's say you are given the opportunity to produce a spike train. You know that you are going to, let's say, run 100 time steps, and you know the time step starts from zero, right? So you use that as a reference, and then you kind of either produce a number of spikes over time, or you plant those spikes into the computer. Is that clear? When you are going to generate the spike train, right? So you kind of start the reference of zero.
There is no timing window.
I'll talk about that, when we come to the learning rule and so on. Right? For now, it's just very broad that okay, you have real value, you just have to encode. And let's say I'll give you 10 time steps you want to encode, and then you figure out where to plant the spikes. Okay? And one other example I would probably want to show is, other example of this coding. Right? So this is a paper that came out of, one of the popular machine learning gurus like Max Willing. What he essentially showed was, okay, you usually have these video frames, right? So essentially there is a lot of, if the background might be stationary between the two. So in the early days, if you were to think about efficiency in computing, if you somehow were able to encode that information, using spiking technique, where, if the real value changes, like here you produce more spikes. If the real value does not change much over time, you kind of spike lesser and lesser. So he kind of applied this technique called predictive coding to essentially encode a real value to a spike train, and all the compute and communication was happening using those spike trains, and eventually he was able to reconstruct and show that okay, the error could be minimal. So the goal here was okay, you wanted to do a real value compute, but then it was efficient if you could somehow translate those to these kind of spike trains, and then you finish your compute, and then he reconstructed back and showed that okay, you do this with minimal error. So this is another application where you can use spike coding to kind of derive efficiency from an implementation standpoint. Is that clear? So it's a very interesting paper in case you want to check it out. Right? They probably do almost the same computation. I will not say exact, right? Because there is some error when you reconstruct. But then this field of approximate computing is where you do some algorithmic optimizations to gain energy efficiency, but then you want to make sure that you gain that efficiency at while having a reasonable accuracy from a performance standpoint. Okay, so this is one such approach where you can use a spike coding principle. So is that clear? Now we'll move on to an actual network with the spiking neurons and figure out how do we now train or infer with such a network. Okay, so there are broadly three training approaches for a network of these spiking neurons. I'll spend a little time on an algorithm called the spike timing dependent plasticity, which is more bioplausible. And then there are two other approaches. Second is ANN to SNN conversion. Let's say that you already have your off-the-shelf trained models available in Hugging Face. Okay, let's see if you can somehow convert them to a spiking network only for efficient inference, right? So that's what ANN to SNN conversion talks about. And eventually, of course, right? So you can do backpropagation, just like how you can do backpropagation for regular deep learning networks. You can also do it for a spiking network. We'll talk about what are some of the challenges there. Okay, first I'll delve a little deeper into this training with spike timing plasticity, because I think that's a very unique attribute or perspective when you have a network with spiking neurons. Okay, so let's look at that. Essentially, I'll first show you an example of how you can kind of achieve unsupervised local learning, right, using a network of spiking neurons. So what is unsupervised? If you are able to achieve learning without having a labeled data set and running an optimization, running a gradient descent algorithm, then it's unsupervised, right? You don't kind of tell the network that this output has this label and now learn with that, right? If you're able to learn without labels, then it is unsupervised learning. Local learning means that you have a weight connecting two neurons, right? So if you can make your weight updates based on information you have locally in the vicinity of those neurons, then it is called local learning, right? If you contrast that with deep learning, let's say you are at layer 2 of a network, you have to hold on to the activations of the second layer until you do your complete forward propagation and wait for the error gradients to reach you before you make an update, right? That's how usually an algorithm like back propagation would work, right? So that's a global learning rule. But here what we are saying is, somehow I do the forward pass in the layer, and once I complete my forward pass, if I'm able to make a weight update, then the learning becomes local. So we'll try to have a very simple example of how we can achieve this unsupervised local learning in a network of spiking neurons. Okay, so I'll talk about what is this spike timing dependent plasticity. As the name suggests, spike timing dependent plasticity is the ability to learn, right? That's a neuroscience term. We say our brain is plastic means that the brain can learn. So if that learning or plasticity is dependent on spike timing, then the algorithm is called spike timing dependent plasticity. So as I said, you have an input neuron connected to a post neuron. Let's say the input neuron spiked, and it caused the output neuron or the post neuron to spike after some amount of time. So STDP says that you measure this spike timing difference and come up with the corresponding weight change and then increment your weight update. So essentially, if there's a causal relationship between your input neuron which causes the output neuron to spike, you know that this input neuron is relevant for the output neuron, right? Essentially, you increase the weight, but the question is by how much do you increase the weight? You measure the spike timing difference and have a rule that says, how to translate this spike timing difference into a weight update. And initial works on STDP would use an exponential curve here, because apparently it was observed in the rat hippocampal brain that someone measured and said that they could do an exponential fit. Eventually you'll see that exponential or what doesn't matter. The key takeaway here is you somehow have to use spike timing, and you can have any kind of function here. As long as you're able to use a spike timing to learn, you can still achieve this unsupervised local learning. Okay, so causal relationship, you increase the weight. How much to increase? You kind of measure the spike timing and figure out the y-axis from here. Okay, and on the contrary, if your input neuron spikes after your post neuron, then obviously this neuron does not cause a corresponding post neuron to spike. So this is like a causal relationship. So in that case, you have to go ahead and decrease the weight. So in the neuroscience term, increasing the weight amounts to, it's called potentiation. You potentiate the weight, and decrementing the weight is called depression. Okay, so this was what was, again, as I said, observed in the rat hippocampus. So what one of our early works looked at it and said was, instead of a multi-bit precision weight between your input and output, if I were to have just a binary synapse, right? What is a binary synapse? It has only two levels, 0 or 1. If I were to have only a binary synapse, can I come up with a learning algorithm based on STDP to be able to have some kind of learning, right? So here our proposal was, if you have a binary synaptic weight, we said the switching probability of that synapse is proportional to the spike timing information. Is that clear? The multi-bit weight, you measure the spike timing and make a corresponding weight change. If you have a binary weight, we cannot do that all the time, right? Because otherwise you always go from 0 to 1 or 1 to 0 all the time. Essentially what you need to do there is you have to switch probabilistically. We said, okay, you have a causal relationship between the input and output neuron. You measure the spike timing, get a probability, and you probabilistically potentiate the weight. So meaning that the weight always does not go to 1, but then you have a certain probability associated with that, so that you can have some meaningful learning, right? If you keep switching all the time, then there's no learning, right? Because if a synapse keeps flipping, you don't have any learning at the end of the day. So you have to do it probabilistically. And similarly, okay, if there's an acausal relationship between your input and output spike, you probabilistically switch the synaptic weight from 1 to a 0. Is that clear? So the key idea here is you have binary synaptic weight, meaning that synapse that connects the input and output neuron or the pre and post neuron is binary, and to have a learning based on spike timing information, we say that we are going to either probabilistically potentiate or probabilistically depress this synaptic weight connecting the two neurons. Okay, let's figure out now. STDP is a learning rule, right? Of course, if you have a network, one is a weight update, but how do we have other mechanisms to make sure that we have a network, different neurons learn different things. Okay, thus we will see. But right now I've told you what is STDP, and if you were to just have a binary synaptic weight, we call it binary or stochastic STDP, where we can still adapt this STDP rule for a binary synaptic weight. Okay, is that clear? So now let's look at a very simple spiking neural network. Okay, this was by the way the state of the art when I started my PhD. Okay, but it's very useful to learn and get some insights out of it. Okay, let's say that I have an input image. Okay, this is your MNIST, one of the images from the MNIST data set. You have the pixel values. Okay, now you have to convert the pixel values to spike trains. Okay, we'll do the rate coding. Okay, and then let's say I have one more layer, and this layer has, let's say, a bunch of neurons, and these are called the excitatory neurons. Essentially, my input is fully connected to every neuron in this excitatory layer. Essentially, we have a fully connected layer here. It's called the linear layer if you have done PyTorch or TensorFlow, right? So you have your input, and you kind of fully connect each pixel in your input to each neuron in this excitatory layer. So what is the goal here? I want and each neuron is, by the way, a spiking neuron here. I want each neuron in this network or in this excitatory layer to spike more for one particular class of input. That is my goal. Okay, let's say how do we do that? So what you have is, let's say you initialize all these weights to random at the start. Okay, and then you show the input over time. We said that okay, we can convert the real values to spike trains, and we are going to feed the spike trains over time, and then the neuron, let's say, will slowly start spiking, and then you measure the spike timing difference, and let's say you have a binary weight, you probabilistically either potentiate or depress the weight by measuring the spike timing information, right? What is the goal here again? Let's say neuron 1 started spiking for this particular input. I want to make sure that I measure the spike timing and update the synaptic weights in such a way that if I were to show similar images of 9 in the future, I want this neuron to spike more. Okay, that is the intent here. And let's say you can do STDP between the weights connecting the input to this particular neuron, and then you can achieve whatever I have said. But wait, there's a problem, right? So if one neuron starts spiking and then you increase the weight, after 9, let's say I were to show 1 or a 0 or a 6, the same neuron, because it has a higher synaptic weight now, will try to fire more and it will want to learn all the input paths. The problem clear? If I don't have any other mechanism that I have shown here, I just show an input. Now look at the spikes of the output neuron in this layer, do STDP. Nothing prevents one particular neuron from dominating your learning process. Why? Because you have no mechanism, right? So this neuron started spiking, it could as well spike for any kind of input you are going to show. If a neuron wants to learn all the classes of input that you have, then you have no learning in your network. Is that clear? Because it will spike for 1, it will spike for 0, it will spike for 6. Okay, what is the learning there, right? You cannot do anything meaningful with that. So essentially, we have a mechanism called lateral inhibition. So what do we do? When a neuron starts spiking, we essentially inhibit the other neurons so that we can have this one neuron which is trying to uniquely learn this input, and not all the neurons would now want to learn the same kind of input. Right? The problem also is shown input, weights are random. You potentially, if you don't have anything here, you could have all the neurons which want to learn all the inputs, which is a situation you want to avoid. How do we do it? You have something called negative or inhibitory connections from this neuron to all the other neurons, so that when a neuron starts firing, it will try to learn something useful based on what you have shown, and it will inhibit the other neurons in the network, so that you can get each neuron to uniquely learn something. Second problem, as I said, now a neuron starts learning, it will become greedy and it will want to learn all the input patterns, right? This one neuron can, throughout your training, can continuously inhibit the others and want to learn everything, in which case you will not have any learning. So what do? We have a mechanism called homeostasis. I talked about this threshold, right? Every time you have to accumulate your information into your membrane potential and fire if your membrane potential exceeds the threshold. So how do I make this neuron that has learned something keep quiet for some time? I'll just increase its threshold voltage. So I'll make it harder for this neuron to spike for a while. So once I achieve, I make any synaptic update for a neuron that's spiked, I will also go ahead and implement homeostasis on that neuron, meaning I'll increase the threshold voltage so that I can keep this neuron quiet for some time and let other neurons in this network learn the different patterns of input that you are trying to show. So the cool thing here is we don't have global optimization, we don't have any error function, we don't do backprop. All we say is, okay, I'll have these mechanisms called lateral inhibition and homeostasis, and somehow I want to introduce the technical term as competitive learning among these neurons, so that each neuron will try to pick up a selective class of input and then spike more for that class, right? That's how we kind of achieve learning in a very simple setting here, which is like a two-layer fully connected network. Is that clear? So let's kind of see what happens during the process of learning. So initially, let's say I have nothing that is learned. I'll just initially randomly have zeros and ones here. So each square is the bunch of weights connecting every neuron here. Let's say I have 400 neurons. It is organized as a 20 by 20 grid, and each small square is all the, let's say MNIST has 28 by 28 inputs. So in each small square, I'll show you the 28 by 28 synaptic weights connecting each of the neurons you have in the excitatory layer. Is the image clear? So I'm trying to show the synaptic representation learned by the synapses connecting the input to each neuron. Right? What is the goal? We want the synapses connecting each neuron to learn a unique class of input with the mechanisms that we have just shown. Okay, so how do I get there? Okay, I got the question. So as I start this process, eventually you can see that different neurons are trying to pick up different input patterns, so that at the end of training you say that, okay, this neuron has learned the pattern 2 more, and this other neuron has learned the pattern 0. Right? That's how you kind of have this unsupervised local learning here. Right? But if you carefully look at this image, right? Again, since we are doing unsupervised learning, a particular neuron, let's say, wanted to learn either a 7 or a 9, and eventually ended up learning more of a 7 than a 9. Right? So in our naive STDP rule, we don't have any provision to unlearn features outside your receptive field. Essentially, if it spiked more for a 7 to learn a 7, you have to unlearn features corresponding to a 9. So the problem was there was nothing there in the mechanisms that we talked about, including STDP, homeostasis, and so on, which will allow the neuron to unlearn whatever is not relevant for the neuron to spike. Okay? So essentially we propose something called a hybrid STDP. By the way, if you have a positive correlation, you potentiate, it's called Hebbian learning because it was postulated by a neuroscientist called Hebb. So anytime there's a positive correlation in the spike timing, you increase a weight, it's called Hebbian learning, right? But we kind of introduced an anti-Hebbian segment to it, we'll go over it. So this was the STDP that I showed you previously, spike timing, probabilistically depress or potentiate the weight. We have an exponential. We realized that, okay, exponential or square doesn't matter. So this was easier to implement in hardware. So we said, okay, we'll make it a constant probability based on spike timing. All I care about is it would probabilistically potentiate or depress. Whether it's exponential or not, didn't really matter much. Okay, and as I said, we introduced an anti-Hebbian depression window because although you have a positive spike timing correlation between your pre and post, I am going ahead and decrementing the weight. This is anti-Hebbian. This is the opposite of what Hebb postulated. Why do we do that? Because if you have a neuron that has learnt a 7 very well, it might still spike for a 9, but the spike timing difference would be larger. So in those cases, if I were to decrement the weight or probabilistically switch the weight to 0, it would be a mechanism that will help me or help the network unlearn the features which is not relevant. Okay. And if you look at the image on the left, this is what was learnt by all those synaptic weights, with the hybrid STDP rule, and you can contrast and see that this anti-Hebbian part that we added to the rule, essentially where you depress, if you have nevertheless by still having a positive correlation, but you kind of do a synaptic depression because the timing difference is large and you feel okay, it is irrelevant. If we are able to implement that hybrid rule, then we are able to essentially get the neurons to learn something, unlearn the features which are not relevant. So with this hybrid STDP rule, we could have a computational accuracy using a binary synaptic weight and learning only using unsupervised mechanisms here. Right? And then we said that okay, you can have this same kind of learning that you could have if you were to have multi-precision synaptic weights connecting the neurons. So even with a binary weight, we show that you can achieve learning with a reasonably good accuracy what at that point in time. Okay, and the problem is, this is good that okay, you're able to use those bioplausible mechanisms to learn, but the problem is this, right? So eventually if you want to move to a complex data set, let's say like a CFAR 10, you want to move to a convolutional network, right? Because convolutional network have been shown, those networks have been shown to work well for complicated images. So now the natural question is, if I were to move to a complicated data set, let's say like a CFAR 10, 100 or even a tiny ImageNet, what is the kind of network I need? Okay, I need a convolutional neural network. The second question is, okay, if I were to have a convolutional network, can I still have STDP based learning using those mechanisms that I talked about? Okay, so that will figure out how do I now apply STDP based learning in a convolutional network. Okay, so let's say that I have a spiking convolutional network, meaning that each of my convolutional layers are made up of spiking neurons, and then I have multiple of them, and then eventually, I'm going to do STDP based training on those convolutional layers in a layer wise manner, right? Because we are talking about unsupervised learning rule. So essentially we try to train each convolutional layer that we have in a network in an unsupervised manner and layer wise manner. And then obviously I can put a classifier towards the end to just make sure that once I have done with my unsupervised STDP training here, I have those feature vectors here, and then I'll train a very simple one layer classifier to provide me the classification output. Is the setting clear? In a convolutional, we want to have binary synaptic weights in those convolutional layers, and then I want to use STDP based training to kind of train those synaptic weights. Once my training is done, I want to have a classifier here by which I'll say okay, which input belongs to which class. Okay, so that's the setting we are talking about. And before I go any further, when I say a convolutional spiking layer, what I mean is, again, have your input, you convert those to a spike train. So image is converted to a spike train. Okay, this is a snapshot at any given instant, and then I'm going to convolve with my synaptic weights. In this case, we have chosen 1 and -1, and then I'll get this membrane potential, and then I'm going to apply the leaky integrationifier nonlinearity. What do? I just accumulate this membrane, this weighted input sum into my membrane potential, and then compare each potential of each neuron here to a threshold, and then produce my output spike. So in a convolutional spiking network, again I have input spike trains, I have the weights, I do my convolution, accumulate onto the membrane potential, compare with the threshold, and I will produce an output spike map. Okay, so is that clear? So this is what we mean by a convolutional spiking network. Okay, let's see how do I now achieve any kind of training here. As I said, okay, you have your input spike map. Let's say I'm showing only one input feature map, one particular weight, and I have, let's say, an output feature map. So what do? If I want to do STDP, I'll look at which output neuron spiked, I'll figure out the corresponding receptive field, measure the spike timing, and then probabilistically flip those weights, right? Looks easy. But in con, we kind of do weight sharing. Essentially the same kernel is going to be slit across your entire input feature map. So what do you have as a consequence? You have multiple neurons in your output feature map that would spike. So what do? You measure this, you again figure out the corresponding receptive field and average out the spike times, okay, and then make one particular weight update, okay. So you have multiple output neurons that spike, figure out which input receptive field is responsible for that. If you have multiple, then average those particular spike times and then come up with your probability with which you want to flip this one synaptic weight. So this is how you can do STDP in a convolutional neural network setting, okay. But we also need those other mechanisms that we talked about, right? Okay, when you have potentially multiple output feature maps that you have, right? So you need a mechanism to make sure that not all the output maps try to learn the input that you are trying to show. So how do we do that? How did we previously do that? We did that with homeostasis, okay. But here the number of neurons in your conv networks are huge, right? So you cannot have a connection from every neuron to every other neuron in your layer. So we said, we drew some inspiration from deep learning. We said, okay, we could do dropout. What I would do is every iteration, I'll randomly drop a few of the maps and I'll kind of encourage competitive learning within the maps that have not been dropped. So that I'll make a STDP weight change only on those maps that have not been dropped. So dropout worked reasonably well as a poor man's lateral inhibition. And we still need homeostasis to make sure that among the feature maps that are active, you still want competitive learning, right? So that not all the feature maps that are active end up learning the same. So essentially we do homeostasis to make sure that when we make a weight change, we still increment the threshold of these neurons so that we can have some kind of competitive learning across the feature maps that we have, okay. So with this, we are able to, I think we are one of the first groups that showed how do we kind of have STDP based learning in a convolutional neural network setting. And we also said, okay, it's good, you can do, let's say 1 layer, 2 layers or 3 layers. The accuracy improved with, ResNet was popular at that point. So you also need residual connections from your input all the way to other layers so that you can have STDP based unsupervised learning, right? But there was a limitation that the accuracy wasn't improving beyond a certain point, and that limitation comes from the fact that STDP is an unsupervised algorithm, and unsupervised layer-wise learning itself has a bottleneck in terms of the accuracy you can get, right? And the intuition is, okay, you have cat and dog images that are similar, an unsupervised learning algorithm will cluster them in the same bin. So now you have to do some kind of global weight update to distinguish and say, okay, although they have a lot of similarities, one is a cat, one is a dog, right? So essentially that aspect was very hard to have in an unsupervised learning methodology, right? So the accuracy being saturating fundamentally stems from the fact that we were doing unsupervised layer-based learning. Essentially we kind of eventually had a methodology where you could start with STDP based pre-training and then we would do some incremental fine-tuning with backprop so that we can regain the lost accuracy. So that's when I think we said, okay, STDP might not be an end-to-end learning method, but it could initialize your weights if you have a spiking network to a good point before you kind of fine-tune with a global backprop so that you don't need to run your backprop for longer. That was one of the proposals we had in this work. So that kind of wraps up the talk on STDP that I gave, and then I'll want to give a slight flavor on what is the state of the art today and what are some of the works that we have been doing of late. Do you have any questions before I move further? Yeah.
So, I didn't fully understand how the synaptic neuron works. So, say a normal perceptron,
Right.
you have your input, say 2,
Right.
you have your weight, say 0.5, and you have a threshold that the perceptron has, say 0.25.
Right.
So, when you multiply the input with the weight, and if it's above the threshold, it
Correct.
Here, say I have the same, say I have 50, the input is 50, and I rate code it.
Right.
And the threshold is also like, what would the threshold be?
So threshold you initialize randomly at the start,
Right.
and then you keep increasing as and when the neuron spikes more, and you stop training at a point where the threshold is reasonably high that the neuron is finding it hard to spike.
So say the input is 50 here, I
Right.
rate code it,
Right.
and threshold is say 20. So after 20 of those spikes, it will fire.
When you have a bunch of inputs, right? So it's,
Right.
it's not like
For
you
a
have one
single-
input.
For a
Correct.
single neuron,
Right.
after say 20 inputs, it will fire.
Right.
So does that mean the spikes that happen near to where it fired will be given a higher?
Correct.
It will be given.
It will be given in the higher rate coding kind of a
So
setting.
each spike will have its own probability.
Right. Because we also have this leaky mechanism in the potential, right? So the potential will also leak.
Right.
In a way to kind of cancel out some of the things that you said. But yeah, so whenever the spikes are close to when the output will spike, then you give it a more weightage. And eventually we came at a point that we said it's a constant, right? If you had an exponential, then what you said is true. And we said, okay, it also works with some constant setting there. So what is important is the fact that you can somehow capture the spike timing information as long as you kind of have some windows, which is like, highly correlated state or a weakly correlated state. That kind of granularity was sufficient, right? It need not be very precisely exponential or whatever. Okay, yeah.
So are you converting the spatial data into spiking map first,
Right.
then do the computation? So
Right.
there are some additional computational overhead, I guess.
That is the input, but eventually the goal here was to, this is a data set that people understand. The goal is we want to do this on a spatiotemporal data like speech or let's say even a video, right? Speech inherently spatiotemporal. So you have input over time already.
For image data probably.
Yeah, image data, it's like a proof of concept that okay, we can kind of do it. As you said, if we really want to run it on a hardware, we have an encoder. For example, any chip that we have, let's say from Intel or some of the startups, they'll have an encoder hardware to convert the real value to spikes. Either you do it offline and give it, or if it's on the chip, you kind of have to convert.
So essentially you are getting the memory efficiency. It's actually a trade-off between the computations and this.
Correct. The pitch here is, even if you convert an off-the-shelf ANN to an SNN, the pitch is, the spiking sparsity is going to be very high, as high as 90%. So that you kind of, do, sparse accumulates over time versus a little bit denser mark, one shot. And somehow you want to eke out energy efficiency because you are doing sparse accumulates over time. So that's kind of the pitch, behind spiking from an efficiency standpoint.
And the update rule, weight update rule
Right.
that you showed at slide
Right.
11 probably.
Right.
That's probably for temporal model, right?
Correct.
So how do we do it for rate models that you mentioned?
I mean, even rate model, if you do rate coding, you will have a certain kind of firing pattern, right? You still have input spikes and output spikes. It is just that at the end of the day, you care about whether if a neuron spikes more for an input, is its average firing rate high enough, right? But the same rule, if you were to apply to let's say a temporal coding, then what you would have to do is change your neuron model to an integrated file, because you don't want to lose that one spike information that you have. And then you can still have an integrated file neuron where you don't leak and lose information, but then you still can do STDP and you can have those weight updates there. But then you cannot have a leaky integrated file model that like what I showed. Usually it's an integrated file.
Same kind of thing can be
Same kind of
achieved
thing.
by binary neural network as well.
I'll talk about the difference, right? Binary neural network, I'll talk about the differences also, because binary neural network is still single shot. Here, binary network will not have a state, right? So essentially it's still the same as what you had, except that you have binary neuron. But spiking neural network offers something more, not only from efficiency, but also recently you are finding that even if it offers you more robustness and so on, because it has a state information which it accumulates over time, which a binary network will not have. So there are some distinctions that you could make. That's a good question, good point, right? Why is a binary network not a spiking network? Because spiking network has a state. Okay, good question. Okay, yeah. Maybe I'll just quickly wrap up, and then because I have only 5 minutes, and then I'll come back to your questions. Okay, I just wanted to cover what is the state of the art that we have today. Okay, and as I said, one common approach that was eventually, we had a lot of work here to see if we have an off-the-shelf trained ANN like let's say VGG or any network that you have for let's say detection, classification, and so on, can we convert to an SNN only for inference? It turns out you can, because as I said, if you use rate coding, there's a statistical equivalence between your ReLU and your integrated fine neuron, because you say that ReLU takes a real input and produces the output. Okay, this is the activation function there, max of 0, x, versus if you have a spiking neuron, you want to make sure that the expected firing rate or the average firing rate of your integrated fine neuron is proportional to the real value that you have when you use ReLU as an activation function. Is that clear? You have ReLU which takes in real input and real outputs. If you want to convert, then you can use an integrated fine neuron where the average firing rate of your output neuron is proportional to the real value whenever you are using ReLU in your ANN domain. Okay. Since we have a statistical equivalence here, you can copy the weights of the ANN and construct a corresponding spiking network. Okay. The only thing you have to be careful about now is how you are going to initialize the threshold, right? So as long as you can initialize the threshold reasonably accurately, then you can say that you can have a situation where the the expected firing rate of this output neuron will be proportional to a real value. Okay, so a lot of the initial works that we did was we can copy over the weights good, but now how do we initialize a threshold so that we minimize the loss during conversion, right? So as I said, initially when we were converted, we got almost this same results as, let's say, a regular ANN if we perform the inference in the spiking domain. But unfortunately, since we are doing rate coding, the accuracy improved as we were showing the image over lot more time steps. Okay, and we figured out one source of that accuracy loss was because whenever the neuron spikes, maybe I've glossed over it, the membrane potential is hard reset to a 0, and then you kind of start accumulating again. Then we realized that the neuron spikes and the membrane potential is above a threshold, but how much above, how much higher is above the threshold is also information that you lose in the vanilla integrated fire model. So we said we came up with this residual membrane potential neuron where we said I will not hard reset a neuron's potential to 0 upon a spike, rather I will bring down the membrane potential by a value equal to threshold, so that whatever residual information I have above the threshold is still maintained. Okay, so this is called the residual membrane potential neuron, and nowadays this is kind of a de facto in most of the works that they don't hard reset to 0, rather they'll just decrement the threshold by 0, and we showed that this minimizes the conversion loss. Essentially, the original network was taking, let's say, 2000 time steps to reach an accuracy. We were able to hit the same accuracy levels using far fewer time steps here. Okay, and the second aspect with conversion is you're trying to do some inference over time, but you're kind of not using the essence of a spiking network, because that can be done only if you are able to train in the spiking domain itself, right? For example, if you were to optimize the inference latency more, the only way to achieve that is you can convert, but you will have to have some kind of backprop that goes on in the spiking domain, so that you can also optimize on, let's say, the spiking sparsity or the inference latency and so on. And the problem with spiking activation is the derivative of the spiking neuron is an impulse, right? Essentially, it's a spiking neuron. You have one at a point where you have a spike, otherwise you have no information. You can try a backprop by implementing this model, you will get NAN in your PyTorch or TensorFlow. Essentially, there is something called surrogate gradient, where you create a smooth approximation around your Dirac delta, so that when you want to do backprop in the spiking domain, you still can have some continuous derivative that you backpropagate, so that you can have some kind of learning. So if you just directly use a spiking neuron, then it spikes or it doesn't spike, then it is discontinuous, it is not amenable to backprop. You come up with a smoothened approximation, usually called a surrogate gradient, so that you can have a gradient approximation for your discontinuous spiking neuron and achieve some kind of learning when you perform spike-based backprop. Another important point to remember is even a feed-forward spiking network will have to do back propagation through time, because you typically show your input over some time steps, and then you have to accumulate the gradient over time. So spike-based backprop can be carried out, but it is expensive from a compute as well as a memory standpoint, because you have to now accumulate the gradients over time. But the advantage with kind of doing spike-based backprop is you can optimize your inference latency. Let's say you want to take very few tens of time steps compared to what you did with conversion, then pretty much that could be accomplished by spike-based backprop. But the disadvantage with doing a backprop from ground up is convergence is a problem, because you are doing now spike-based backprop through time. So what we proposed was, your starting point should be, let's say you want to have an SNN at least for, let's say, image detection and classification tasks. The starting points are weights from the off-the-shelf trained ANN, and then you can do this expensive backprop over very few epochs, so that you can optimize for your inference latency or spiking sparsity and so on, so that you can get the best of what the SNN has to offer for you. And again, this is kind of a de facto in today's, if you look at any gate, especially when they have a network, they usually start off with training it as an ANN, copying over the weights, and then do this incremental, usually backprop, from the spiking domain, so that you can optimize for the other factors that you want to. Is that clear? So essentially, we showed that if you naively, train it as an ANN convert and reduce the number of time steps, you suffer a loss. But then somehow you do this incremental backprop and you regain some of the lost accuracy that you have. So by far, as I said, this hybrid method kind of works well in case you are looking at efficient inference in the spiking domain, and ANN conversion in conjunction with backprop is kind of today's state of the art, at least when it comes to this image recognition and classification problems. And again, before I leave you, I think if you were to implement this spiking network on a GPU, I mean, it's not very efficient. You cannot see the efficiency gain here. So usually you have something called a neuromorphic hardware. IBM has their offering called True North. Intel has Loihi. I think Intel is now the big champion for this neuromorphic hardware called Loihi, where they have asynchronous architecture where they don't have a global clock, right? Essentially, their hardware is amenable to algorithms that are event driven and spike based. So essentially, the neuromorphic hardware is a good match for an algorithm like a spiking network, and right now Intel is kind of driving it, I would say, in a certainly big way. So they're trying to ask researchers to come up with this killer app that can use Loihi and show efficiency on top of what existing deep learning models could do. Is that clear? So if you want to translate the efficiency, let's say, that spiking network offers you, then you have to implement it on a neuromorphic hardware for the best benefit. And again, as I said, IBM was one of the early players here, but at that point I think it was very early, premature, that no algorithm was there. So Intel probably was at the right time in the sense that okay, at least algorithm was mature to a certain extent, and they wanted to be the NVIDIA for neuromorphic. Right, like NVIDIA came up with the GPUs, and then that drove algorithms, and algorithms drove the hardware development in some ways. So Intel is trying to be that for neuromorphic, so that if you have a hardware, then you can have algorithmic innovations which could drive more hardware development. That's kind of the goal here. And yeah, so if we were to give you, some of the key takeaways here, in SNN or spike-based computing, you do computing in a sparse manner using spikes. Okay, both the algorithm and hardware, they lend itself to event-driven spatio-temporal data processing. Like event-driven because the communication and computation happens if you have an event or a spike. Okay, and third is HTTP-based learning was what brought SNNs to the fore, but of course they have a limitation. So right now, at least the state of the art is okay. You have the combination of conversion and spike-based backprop, and of course this kind of algorithms are very amenable to let's say an asynchronous event-based hardware, but of course we need a killer app so that we could champion its widespread use and go on. I think I'll stop from here, and then if you have questions, I have some future directions that we kind of are exploring right now. So with that, I'll conclude my presentation and take some questions. Thank you.
Yes, thanks. Gopal? Yeah, I think we already had some questions here. Yes. Yeah.
Good morning, sir. So I had one question. In the first slide when you mentioned spiking neural network, so you mentioned there's a MAC operation happening to the input spikes, right? So what is it?
In the deep learning case, there's a MAC because you are usually continuous real valid inputs and weights, so you have to do a MAC, multiply and then accumulate. Spiking, I said, okay, you have only zeros and ones, so you do only an accumulate operation. So you kind of, it's a one, you just add the weights, otherwise you don't.
And for how many times that?
So that depends on the application again, right? For example, the state of the art now is within 4 time steps, at least on data sets like CFAR 10 and 100, you get a good accuracy. ImageNet takes like 16 to let's say 256 time steps if you want. And of course, if you look at an application like speech, time steps comes with the data set itself, right? So you measure, and you get the, we had some process talking about the MEL spectrogram, right? So that is some, data set you get over time. So kind of time is also determined in a spatio-temporal application with the data that you have and your sample weight itself.
So also, I had another question. How are weights updated in STDP and in SNN-based CNN?
So again, I think that's what I tried to convey, that okay, it's easier to envision STDP in a fully connected setting because you have unique weight connecting an input to an output neuron. In a convolutional spiking network, the problem is, I'll not say a problem because the weights are kind of shared. For each neuron, you have weight sharing that is going on, right? For each map. Essentially, you kind of look at the spikes and then you have to average all those receptive fields to come up with one average spike timing, and then you make a weight again. Essentially, for fully connected, you have a unique input weight, unique weight between every pair of inputs, right? In a convolutional network, you have weight sharing, so you have to average out the spike times and come up with one update.
So, like, my question was like in the normal neural network, you have a back propagation step where you're trying to optimize a cost function and then assigning the weights.
Correct.
So how are the weights assigned here?
So here you just measure the spike timing, right? You show the input, the output spiked after some time, you measure the spike timing and then you make a proportional weight change. So it's with this spike timing.
Also, how does the hardware for this?
For temporal you were saying.
For temporal, and even if you do a rate coding, right, you still have the spike timing information. But what you care about is average rate. Although your STDP itself will be made with the spike timing information. Even if you do rate coding, you still have the spike train over time, right? So you still measure the spike timing, but you want the output neuron to spike enough number of times so that it's proportional to the input value you are encoding something. Right? You can still do STDP that way. Temporal, it's all the more important, and you have to be careful about what kind of neuron model you are trying to use, so that you don't leak and lose that one spike information that you have.
So one last question: how does the hardware for this look like?
So I think you can, I can point you to Loihi, or there's an offering called Akida from a company called BrainChip, right? So they kind of, at least Loihi, I mean, usual accelerators, right? You have a global memory, you have a bunch of processing elements, right? But in a neuromorphic accelerator, you will not have a global memory, right? You have a processing element called a neuron, and they have each neuron has some kind of local memory. So that's what distinguishes the neuromorphic versus traditional accelerator that you have. Almost any accelerator has a bunch of processing elements. You have a global cache that is shared, and it's very easy to write software for that. Pretty hard for neuromorphic because you want to avoid this. So each processing element has its own local memory, and that's it, right? Okay, and it's a challenge, right? So that's how it looks. And Loihi at least is asynchronous. They don't have a global clock. It's like globally asynchronous, locally asynchronous kind of a thing, right? So now any chip, clock tree consumes a lot of power. So they have built asynchronous chips, which is a challenge. That's an engineering challenge that they have solved. But how useful it is, I think we'll figure out with the killer app. But building an asynchronous chip is a huge challenge.
Good morning, sir. So as you mentioned regarding one of the hybrid model that is called as Hebbian plus and Hebbian. So what is the main parameters you would consider as unsupervised?
So the parameters you're talking, what are the hyperparameters as far as the learning rule is concerned?
Yes.
It's basically the switching probability.
That is called as alpha value. What is the category will be followed? 0 to 1 point up to.
Yeah.
So
Essentially you tune whatever is the probability so that you can still kind of not rigorously go from 0 to 1, right? So one hyperparameter you have to tune as far as this hybrid STDP is concerned is what are your potentiation and depression probabilities.
yes, that is the first one. The previous slide is mentioned as unsupervised with
Correct.
K-means clustering algorithm.
Similar to, I said it's similar.
Yes, similar to only.
Correct.
The K-means is
Correct.
what kind of distance measures you have proceeded.
So here as I said it's based on spike timing, right? K means you measure. So here I'm saying to give a flavor it's similar to a clustering algorithm we have. Here I think we kind of cluster based on what class a particular output neuron spikes more for, right? So essentially you have 100 neurons, you have 10 neurons that will spike more for, let's say, a 5 or a 7. So we say that we group all those neurons that spike more for a 7 and we call it a cluster. So here the clustering happens using the spike timing information with the other mechanisms that we have.
Yes, that is a basic neural.
Correct. Yeah. So
whenever include that convolutional neural networks, now coming to picture the convolutional neural networks, residual stochastic convolution network
Correct.
you have considered.
Correct.
That is a one category, two category, I mean one convolution layer,
Correct.
three convolution layers, so that you are extracted feature maps.
Correct.
In that feature maps also you proceed with unsupervised.
Correct.
In the point of view as mentioned, bottlenecks.
Correct.
So what kind of features you have proceeded, sir?
So you're saying what are the bottlenecks for unsupervised learning in convolutional networks?
Yes,
right?
yes.
The first bottleneck is you cannot make it arbitrarily deep because unsupervised learning will itself have a limitation, right? So if you make layers, let's say 3 layers or 4 layers deep, you need some kind of a global update to make sense of the additional parameters that you have. So one limitation or bottleneck is you just cannot do unsupervised STDP and make the layers arbitrarily deep. That will not improve your accuracy, right? If you want to improve, you have to have something called a reward moderated STDP where you are at least able to take some global, not like gradient, but some kind of a reward so that you can make a better weight change to your additional weights you have added and have improved accuracy. If you just implement the plain STDP, it will not work that great. If you expand, that's one of the bottlenecks.
Yes. One more article so you're showing like as a CBT.
Correct.
The particular paper also is clearly mentioned regarding resident with the stochastic. When I move on stochastic gradient descent point of view, when accuracy will be standard. There is no changes for accuracy. There is good accuracy. What kind, when increasing of loss functionality, what kind of parameters you have proceeded? Hyperparameters.
In spike-based backprop you're saying?
Not back propagation. What kind of whenever included stochastic gradient descent point of view, what kind of hyperparameters? Because of when I move on that exploitation, so difficult to see these kinds of
stochastic gradient descent, you have the usual ones, right? You have to have a learning rate scheduler, then you have to essentially figure all those out.
Yes, that is the reason you clearly mentioned dropout is output is equal to 0.
Sure.
In the particular slide.
Which slide maybe?
One slide is clearly mentioned dropout. That time only clearly mentioned regarding the gradient descent.
Oh, okay. I think this one, huh?
Next slides. Next slides.
Okay.
Next slide, sir. I think this is the last function. It is before that only. As mentioned, dropout is equal to 0.
Dropout is equal to 0. Is this the one?
Yes, yes.
Okay.
Dropout output is equal to 0.
Correct.
So in this case, whenever extracting the features learning,
Correct.
so what kind of measures you have proceeded for the increasing of loss functionality? You have
Okay,
mentioned
so
the
here
dropout.
actually there's no loss, right? We are still in the unsupervised territory here.
Yes.
Here, since we don't have a loss, what we said was ideally we would have to have a mechanism like inhibition, wherein one map spikes, it could inhibit the other maps. Here we said that's very costly to implement because you'll have too many connections and it's very hard to get it to work. Essentially, dropout is you just randomly drops off the map so that you can have competition between the maps that have not been dropped.
Okay.
Right? Here you just tune the dropout ratio to whatever.
Yes, that is the reason he has mentioned the limitation of celluation.
Right.
Yes, correct, sir. So, but my question is related to whenever we want exploitation, especially the conventional neural networks digital bit, that is a 34, 80, 51, 101, 151, any category.
Okay.
The number of layers.
Okay.
So, with followed by the stochastic point of view.
Okay.
What kind of measures he especially proceeded for the decreasing of loss?
Now here, as I said, if you want to improve it, you have to combine it with a supervised training methodology.
Okay,
Right?
thank
So
you, sir.
unsupervised itself will not do the cut for you.
Yes, sir. Thank you, sir. Thanks so much, sir.
So if the data set is complex, which is having contextual information, say for example, background is not that clear,
Right.
how does this spiking method perform?
So all those cases, you have to, as I said, you have to start with conversion and do this spike-based backdrop, right? So SCDP itself has a limitation because, as I said, we are trying to introduce some mechanism that we know happens in the brain to see if we can do useful compute. But as long as your data set becomes complex, at least the best way we know today is start from a good starting point, initialization, and do spike-based backdrop and focus on other aspects like, let's say, efficiency. Or we have recently been finding that doing this in the time domain also gives improved robustness, both adversarial and other ways, which I didn't have time, but we are looking at the security as well as the efficiency aspect of having this spike-based inference. It's not only an efficiency pitch, which is what it used to be until now. The natural question is, okay, what more does it offer, right? It almost seems like we are playing a catch-up game, right? So what more is something we are trying to answer now in terms of, let's say, the robustness or tolerance to some kind of attacks that we have been very actively exploring on the security front right now. So to answer your question straight, any complex data set, you have to do some kind of spike-based backdrop, okay? But pitch it in by also studying the other robustness and other aspects so that you don't only are harping on this efficiency, but you also bring about what is unique if you kind of infer it in a certain way, in this spiking domain. That we have seen, I think security is one promising direction that we are seeing.
Do you have some evaluations on the energy efficiency of these STDP?
So I'll answer it in two parts. For longest of time, since the algorithm was not mature, we are just trying to improve the algorithm. Now I think the algorithm have reasonable maturity. I think Intel Loihi, they might have some kind of benchmarking on how much efficiency you can eke out. But in our lab, we are kind of building accelerators which can accelerate both ANN as well as spiking domain. And right now we are gravitating more towards a hybrid model. Like we are seeing like hybrid ANN and SNN is kind of working the best. We'll have the result shortly. So we kind of built an accelerator that can support both ANN and SNN and trying to see which to benchmark ANN standalone, SNN standalone and see this hybrid and see what works with this. So right now I think any benchmark number you will probably find in papers like Loihi where they'll give you the energy numbers for some of the standard data sets. But from our group we are kind of having our own accelerator right now to kind of benchmark the same.
It's having lots of exponential operations, I guess.
Which one?
This spiking neural network.
But I think you can simplify the neuron model, like leaky integrated fire might not always be needed. For example, for all practical cases, we kind of do a very simple integrated fire where you don't have the exponentials. But yeah, that all the initial works was because leaky integrated fire is a more, bioplausible model. That's when it started, and it offers you unique characteristics. But as from an implementation standpoint, you want to cut down on, any inefficiencies you have and have some bad, From that perspective, we have seen.
You're doing the approximation.
Yeah, doing approximation, and yeah, as you said, right, Loihi works because exponential is inbuilt in the neuron model. Intel's Loihi, they don't do it separately, right? If you do it in GPU, then you have to run the exponential separately, but if you have a neuromorphic hardware, they give you the exponential inbuilt into your hardware. So you can map your neuron to one neuron in their hardware, and that will do the exponential leak dynamically, which is more efficient than trying to use a general purpose compute for doing the same.
But you lose the accuracy.
Little bit. No, it's always a trade-off, right? If you use leaky integrated fire, you get more sparsity. Right? But it's also harder to train, and you also have complexity in terms of the neuron model itself. Versus you just simplifying, maybe not that sparse, but still gives you a good trade-off between, let's say, sparsity and accuracy.
I had a question which is very much regarding the training of spiking neural network. So you showed the 20 cross 20 grid, and in that the image was like each grid is a neuron, right? So
weights connecting a neuron.
Okay. So the image is fed to that. It's not pixel wise.
Right. So essentially your input is, let's say, 20 by 20. Let's suppose our input is 28 by 28. What we are trying to show is that 28 by 28 weights connecting each neuron. If a neuron spikes more for 7, you want the weight to have some general representation of a 7. It should not be one particular 7 you showed in your training set. So the 7 or anything it learns should be a general representation, so that any kind of 7 you show, this neuron should be able to spike more.
Okay.
Yeah.
So regarding the application of SNN, sir, can we apply this for the biomedical signal processing example for ECG or like?
Yeah, I think you should email me, right? I think it's very suited for data that is inherently spatio-temporal, right? So we are trying. The works have been done in terms of ECG classification and so on to detect, let's say, some heart ailments. The work has already started. So people are trying to figure out what is the killer app where you can use, where, as I said, you don't convert something as a real value to a spectrum. Rather, you have some spatio-temporal input, but to publish to the community, right? Community does not understand ECGs. They understand the standard data sets well. To show a proof of concept, we will do whatever the community wants, but the actual application is now you have the algorithm, now you have the reasonable maturity, and then you actually take a real spatio-temporal data set and show it, right? But if you do only this, I don't know if you can publish it. You have to do what the community wants. Right? That everyone understands. Right? If I say imagine, everyone understands. Okay. If I say ECG, okay. It's like the joke yesterday, right? Okay. But yeah, it's geared for spatio-temporal data. That's the initial work, sir. If you're interested, I can point out, and yeah. If you're more interested, you should write it.
Yeah, good morning, sir.
Yeah.
My question is that for the surrogate gradient-based backpropagation to drive, what was the purpose of using the direct delta?
Okay, so essentially you have a spiking neuron. If you just calculate the derivative, so a spiking neuron can be modeled as a Heaviside function. The derivative of a Heaviside function is the Dirac delta. So if you now feed it in, you can do it in PyTorch, by the way. Just model a spiking neuron in PyTorch, there will be no other, except that your loss doesn't go down, right? Because you will say NAN for the autograd will complain that the gradient is NAN. Okay. Essentially, to avoid the situation, we kind of create a smooth approximation around the Dirac delta, so that you feed some real values that make sense during your back propagation. Right? You have to back propagate the gradient of the loss with respect to the output of a neuron, and then you have to multiply it with the derivative of the output with respect to the input of the neuron to move back. Right? This is where we are doing our surrogate gradient-based approximation, so that your autograd does not complain.
Okay. So I know there are many other questions, but also the tea is getting cold. We'll stop here. Let's thanks again, Gopal.
Thank you.
So a small memento from the department.
Just put it here.
That's it.